So good day, everyone. I am John Macedo, second year ECE college student at the School of EECE. In this video, we will be discussing modulation and specifically angular modulation. So we will be defining terms and solve problems along the way. So let us begin. So what is modulation? So modulation is a process of changing the characteristics of the wave to be transmitted by superimposing the message signal on the high frequency signal. So by superimposing a message onto a high frequency signal known as a carrier wave or a sinusoidal wave, video, voice, or other data can be transmitted. So here are the different examples of modulation. So we have amplitude modulation, we have frequency modulation, digital modulation. So those are all analog modulation. Okay. So we have here the types of modulation. So we have here two general types of modulation. We have analog modulation and we have digital modulation. So in analog modulation, we have amplitude modulation, frequency modulation, and phase modulation. On the other hand, we have digital modulation, and we have digital modulation, we have amplitude shift keying, frequency shift keying, and phase shift keying. So the difference between this is that analog modulation uses a sinusoidal wave, while the digital modulation is composed of binary, the one and zeros that represents the waves. So, but in this video, the scope of this video will only tackle about the analog modulation and more specifically, we will only discuss frequency modulation and phase modulation. Well, although we'll be discussing a few information about amplitude modulation as well. Okay, next. So as I said, frequency modulation and phase modulation are angular modulation. So we will know why is it called angular modulation. Okay, so analog modulation. So a continuously varying sine wave is used as a carrier wave that modulates the message signal or data signal. The sinusoidal wave's three parameters can be altered to get modulation: their amplitude, frequency, and phase. So as you have seen earlier in the types of modulation, we have FM, PM, and AM. So those examples. So we have here amplitude modulation, which is where the amplitude of the wave is modified, and we have here the frequency modulation, where the frequency of the wave is altered while the amplitude and frequency stays the same, the phase stays the same. And we also have the phase modulation, where the phase is altered while the amplitude of the wave and the frequency of the wave remains the same. So in this picture, the phase modulation is not quite evident. The change is not it's not visually visible, but in the later discussion we will be able to see it more clearer. Next, okay. So amplitude modulation is the method of varying in the instantaneous amplitude of carrier signal accordingly with instantaneous amplitude of message signal. So the amplitude of the carrier wave is varied in proportion to the message signal, and the other factors like frequency and phase remains constant. So we have here its spectrum consists of a lower frequency band, upper frequency band, and carrier frequency band. So this is the bands that are present. The upper and lower bands is called the sidebands, and we have the carrier frequency, which the frequency that helps to transfer or to uh, transfer the message into the receiver. So this type of modulation requires greater bandwidth, more power. So the downside of amplitude modulation is that filtering is very difficult in this modulation. So a high energy wave is characterized by a high amplitude, and a low energy wave is characterized by a low amplitude. So we have here, the picture we've seen earlier, we have here the amplitude modulation. So the pink line you see here is the envelope. So this is the form. This is what forms in what is should be observed in the amplitude modulation, the envelope. Okay, so Next. So in an amplitude modulation, so as we can see how a how is amplitude modulation works. So we have here in the first one, we have here the message signal. So this is the raw information. This is the message signal. Then the carrier signal, this is the signal that will help transfer the message signal into the um, communications channel. So when the message signal is imposed to the carrier signal, um, it what can be observed is that the amplitude of the carrier signal is similar to the message signal. So the amplitude of the modulated signal is similar to the message signal. So the amplitude contains the information. The modulated signal contains the message signal that is in the carrier signal. So this amplitude modulated signal is a signal that will travel in the communications channel. So this is a frequency spectrum. So as we can see here, we have here the -1 kilohertz and +1 kilohertz. So those are the two sidebands, while in the middle is the carrier frequency. So it can be seen that for a case where there is 100% modulation, M1, and where the carrier is not suppressed, A1, then the sidebands have half the value of the carrier, the quarter of the power each. So as you can see, the perfect modulation where there is a value of one as a modulation is there is the side must have value of the carrier. Okay, so we will now be proceeding to the frequency modulation. So this will be the topic of our discussion in this video. So the frequency modulation, so FM or frequency mod is a process of varying the instantaneous frequency of carrier signal according to the instantaneous amplitude of message while maintaining other parameters on. So previously in the amplitude modulation, the amplitude is modified in the modulation, but in frequency modulation, as the name itself states, the the property that's being altered of the signal is the frequency of the carrier signal. So that will in accordance with the message signal to maintain while maintaining its parameters constant. Okay. So the frequency of a wave is the number of wave passing a point in a certain time. So the advantage of FM over AM is the greater suppression of noise at the expense of bandwidth in FM. It is used in applications like radio, radar, and telemetry, seismics, prospecting, and so on. So the efficiency and bandwidth depends on the modulating index and maximum frequency. So I forgot to mention that in analog modulation is the analog modulation such as AM, FM, and PM is more sensitive to noise. So if noise enters the system, it persists and gets carried till the end of receiver. So therefore, this drawback can be overcome by the digital modulation technique. So that's why the modulation, I mean, that's why the digital modulation was invented. But of course, we will not be discussing that because the scope of this video will only focus on angular modulation. But that's the drawback of analog modulation compared to digital modulation. As the noise is constantly carried from the receiver when once it enters the communications channel. Okay, so going back to the frequency modulation, as what I have said, the efficiency of bandwidths depends on the modulation index and maximum modulating frequency. So let us proceed to the mathematical equation. So okay, so we have here the amplitude. Okay, so this is before in the amplitude, this is the message signal, and this is the carrier signal. So here. So as you can see that when in the frequency modulated wave, uh, there is no envelope like the amplitude modulation. What we can observe here is the increase in frequency and decrease in frequency. So when the message signal is in the positive wave or there is in a positive wave, there is an increase in frequency, while when it goes down and it is on the negative, the frequency decreases. So as you can see, the wide distances between waves and the the increase, the shortened distance of the wave indicates the increase in frequency the wave, as because the wave of the message signal is on the positive. So this one, so this is the mathematical expression, and then as you can see on the right side there, this is also the frequency domain of the frequency modulation. Okay. Okay. So for the formula of the instantaneous frequency is Fi is equal to Fc plus K sub F mt. So we know the relationship between angular frequency omega I and omega theta I t as omega I d theta I t at d over dt. So this is derivative. So we substitute the value of omega I to 2 pi fi, uh, and then we manipulate the equation, and then we will come up with okay. So we now substitute fi value in the above equation, and we will have 2 pi the derivative of fi dt. We will I sorry the integral. Okay, and then we will now be okay. So we see here that there is the value of the instantaneous frequency. So in this equation, we will be plugging in this value into the equation. So in this part, we will be finding the integral of fi, which is the which is in this one. So our formula for now is theta it theta sub it is equals to 2 pi the integral of fc plus k sub f mt dt. So by formulation, this is the this is our problem. This is our equation now. So we now have theta it equals to 2 pi f sub t plus 2 pi k sub f, the integral of mt dt. So st, so we substitute the value. We substitute the value of theta it in the substandard equation of angle modulated wave. So we now have here a sub c cosine of 2 pi f sub c t plus 2 pi k sub f, the integral of mt dt. So if the modulating signal is mt equals to a sub m cosine 2 pi f sub mt, then the equation of the fm will be this one. So this will be the final equation of the frequency modulation, where S St is equal to a sub c cosine of 2 pi f sub ct plus beta sine 2 pi f sub mt. So this part is this one is the modulated. This represents a modulated signal of no, yeah, the modulated. This is the carrier signal. So where B modulating index is, excuse me, change in F over Fm equals to K sub F AM over Fm. So as you can see here in the again in the frequency domain, we have here the multiple modulation. We have here the lower sidebands, and we have multiple upper sidebands as well. Okay, so we are now here in the frequency modulation index. So the formula, okay, from the formula and definition of the modulation index, there is no term that includes the carrier frequency. This means that it is totally independent of the carrier frequency. So our formula for frequency modulation index is equals to m the frequency deviation over modulation frequency. I said that that carrier frequency is not included because in amplitude modulation, plays a big part in modulation of the modulation of the amplitude modulation, the modulation index of the amplitude modulation. Okay, so we also have here the frequency deviation. The frequency deviation will vary according to the level of the audio at that moment. So also the modulating frequency will vary, as normal audio consists of a variety of frequencies which vary to the given to the prior to the speech or music or etc. So the frequency deviation and frequency modulation is index is somehow similar with each other. The deviation just um, finds the maximum maximum modulation index. So this is similar. So in this formula, we just added the maximum frequency deviation over maximum modulation frequency, uh, the signal. Okay, so let's have a problem solving. Okay, so an FM signal is defined by the equation E sub FM is equal to 40 sine 93 times 10 raised to 6 t plus 15 sine 4000 t. So this is quite a equation. So by knowing this equation, this composition of what those numbers represent, we will be able to disseminate the values, and we will find the values that we will need for us to solve this problem. So what do we need to find? So of course this is the equation. So this is the this equation is a general equation that will represent the equation above. So we will be with this we will be easier it will be easier for us to solve for the missing of the problem. So what is needed to find in the problem? So we need to find the modulation frequency, we need to find the modulation index, and we need to calculate the frequency deviation. Okay, so first we find the modulating frequency. So as we recall, the formula for the modulating frequency is okay. So our omega m is 4000. That's as we can see in the equation, it is equivalent to 4000. So it is always it also equal to 2 pi fm. So in this equation, the modulating frequency is in the problem. Okay. So for us to find the modulating frequency, we will isolate the modulating frequency into this equation. So therefore, we will be doing is to divide the 4000 over 2 pi, and we get the modulating frequency, which is 636.62197. Next, so the modulation index. So it is given in the equation, so we no longer have to find that. But so it saves us time that we know that the modulating index is present in this equation. Then next, the frequency deviation. So the frequency deviation is this formula is mf equals to deviation over fm. So the frequency deviation is what is we need to find. So but we now have the modulation index f, which is 15, and we have the modulating frequency, which is 636.6197. So by simple algebra and isolating the frequency deviation, the value we will be coming up is 9549.296,586. Okay, we will now be proceeding to the frequency bandwidth. Okay, so the bandwidth of an FM signal depends on the modulation index MF is approximated by the well-known Carson's rule. So what is the Carson's rule? So okay, so bandwidth is equals to 2 times the deviation plus f maximum FM. Okay, so frequency bandwidth where FM max is the maximum frequency of the modulating signal. Okay, so the factor 2 in the equation is to account for both the upper and lower sideband. So this is left and right of the carriers as we have seen in the wait now in this um in this. So we have here we have here the lower sidebands and upper sidebands. So those the number 2. So the presence of 2 in the equation of frequency bandwidth represents those sidebands. Okay, so we will now be going back to our presentation for a moment. Okay. Okay, so ayan. Okay, so as I said, this equation gives the bandwidth which contains 98% of the signal power. Okay, so as I have said, is that okay, so this is the FM spectrum levels for MF, which is 0 to 15, not in decibel, and a negative sign means a phase of 180 degree with respect to other components. So let's have a problem solving. So an Ann Arbor station 107.1 FM broadcasting at 107.1 megahertz with a power of 50 kilowatts. The bandwidth of the modulated signal is from 30 hertz to 15 kilohertz, which is excellent for high fidelity broadcast. The maximum deviation set by the FCC is 75 kilohertz. We need to find the maximum deviation and bandwidth using Carson as we presented the previous slide. So let's start. So for us to find the bandwidth, we must first find the max deviation. So all in this problem, all the numbers that we need for the max deviation is present. So let's find the max deviation. So okay, so MF mean is we will be dividing the maximum that we have here. We have here 30, modulating is 30 hertz to 15 kilohertz. So we will be dividing the 75 kilohertz over 15 kilohertz, which is the maximum um, range of the FM. So we will be having five. So the both kilohertz will be will be cancelled. So we this five is unitless, and we have here 75 kilohertz. So be mindful of the prefix. So in 15 and 75, they are both in kilo. But in 75 and 30, the 30 has just hertz, but the 75 is in kilohertz. So if we divide them directly 75 over 30, we will get a different and wrong answer. So we be mindful of the unit. So 30 we will move them to the equivalent value of 30 hertz of 2 kilohertz. So with that, we will have a 2,500 answer for FM of 30 hertz. So with this answer, we will now be able to compute for the bandwidth of FM using Carson equation. So the bandwidth of the max, which is involves here, is we have 2 times the deviation plus FM max. So we have computed here is that um, 2 times 75 plus 15, that gives us 180 kilohertz. That is the total bandwidth of the FM. Or per sidebands, they will be distributed equivalently 90 kilohertz each. So it's the lower and upper sidebands will have 90 kilohertz each. And then the other sidebands, the 2 times delta, the minimum frequency modulation is 2 times delta FM mean, which is 2 times 75 of plus 0.030 will give us 150 kilohertz or 75 kilohertz on each side, which tells us that the both each side bands will have 75 kilohertz on each side. Okay, so we will now be after discussing the frequency modulation, we will now be proceeding to the phase modulation. So, excuse me. Phase modulation is the process of varying the instantaneous phase of carrier signal accordingly with the instantaneous amplitude message signal. So the phase of the modulated wave has got infinite points, where the phase shift in a wave we can take phases. So the instantaneous amplitude of the modulating signal changes the phase of the carrier signal. So when the amplitude is positive, the phase changes in one direction, and if the amplitude is negative, if the amplitude is negative, the phase changes in the opposite direction. So as the wave changes positive to negative, the phase also changes accordingly. So phase modulation is calculated by adding the baseband signal to the argument of a sine or cosine function that represents the carrier. So as you can see, we have here the voice phase modulation, and as you can see, this is the same picture as the earlier slides. Okay, next. Okay, in phase modulation, modulation index is directly proportional to modulating voltage, only while in frequency modulation, modulation index is also inversely proportional to modulating frequency. But this is a very important concept for us to remember. So this is a better representation of a phase modulation, where we can see the phase modulation, the phase shift in the carrier modulated signal. So this is a pulse train baseband signal. So this is a digital one. This is not an analog. This is a digital modulation, but this will help us what happens to phase modulation. So as you can see, in the baseband signal XT, when the line goes to goes down, in the PM signal, the there the PM signal changes in phase. So when the baseband signal, when the signal goes to positive, it changes signal, and the same process repeats itself. As long as the baseband signal changes, PM signal also changes in phase. So this is also for sinusoidal baseband signal. So yeah. So as you can see, the phase shift is not really evident in analog modulation, but if you take a closer look, you will see the direction of the phase shift of the sinusoidal. Okay, so let us now discuss um, phase deviation. Okay, so we have here the phase deviation formula. Um, where the first part is the peak frequency deviation of PM waveform, which is in hertz. The K sub 1 represents the deviation sensitivity of the PM modulator. It is computed, and its unit is in radians. And V sub M is a peak modulating signal amplitude V, and FM is a modulating signal frequency. And the phase modulation index, um, the phase modulation is K1 times multiplied by Vm, which is quite similar to the um, phase deviation. So there are actually quite many similarities between FM and PM, but there are also distinct differences between them. The first is that modulation index and phase modulation is actually the same. So technically, if you get the phase modulation or the technically, if you get the phase modulation or the change in phase in EM, that would also be its modulation index. And once you get the modulation index or phase modulation index, that would be the time that you will be able to get its frequency deviation. So a change in phase in PM is it also exhibits a change in frequency and vice versa. So we will be starting with the phase modulation problems. So let's have here. A PM modulator has a sensitivity deviation of 2.5 rads per volt. So if the modulating signal voltage and frequency is 4 volts and 40 kilohertz respectively, determine the phase modulation index and frequency deviation. Okay, so let us first solve for the modulating index. So as we remember, the modulating index is K1 PM. So our K1 is, sorry, excuse me, sensitivity deviation is 2.5 rands. We will multiply that to the modulating signal voltage, which is 4 volts. So simple multiplication, we will be having a 10 rads as the modulating index of the phase modulation. So next, we will now be solving for the frequency deviation. So the frequency deviation formula is the deviation is equal to, we will multiply the sensitivity deviation, multiply the modulating signal voltage, and the frequency. So what we did in the modulating index is we already multiplied K1 VM. So we will now be just needing to multiply 10 rads to 40 kilohertz. So as you can see, it's just normal multiplication once again. We will multiply 10 rads to 40 kilohertz, and we will be having 400 kilohertz. Okay, so let's just solve for the bandwidth. So the bandwidth, as is also in the Carson law, we'll be using the Carson's law. So this is a different form, but it's just the same. Okay, so the bandwidth is we will multiply 2 times Fm plus Fd. So again, we will be just substituting the values. We have 40 kilohertz as the frequency, modulating frequency, and then we also have the 400 kilohertz for the frequency deviation. Now, again, be mindful of the prefixes. So we can observe is that 40 and 400 are both in kilohertz. So we can just simply add them. But if one of them is different, has a different prefix, so we should first convert them, so we will not be coming up with a different answer, or we will have a wrong answer. So since they are both in kilohertz, so we will just simply add them. So we will have 40 plus 440 kilohertz, and we will multiply them to 2. We will have a bandwidth of 880 kilohertz. So as a summary of our discussion, in AM we have amplitude of carry. We have AM, FM, and PM. So amplitude of carrier waves varies as per amplitude or voltage of modulating signal input, and for FM, frequency of carrier wave varies as per voltage of modulating signal input. Phase of carrier wave varies as per voltage of modulating signal input. So carrier parameters we have here in AM, frequency of carrier wave is kept constant. So FM, we have amplitude of carrier wave is kept constant. So PM, amplitude of carrier wave is kept constant. Okay. So in types, we in AM we have different types. We have double sideband suppressed carrier, single sideband. We have vestige sideband, and then there are many more. So this is for DSP, SC, and for FM we have FSK, GFSK, offset, and many more. And for PM, digital PM types include PPSK, QPSK, QAM, combination of amplitude and phase modulation, and many more. So that concludes our discussion. Thank you for listening, and I hope I was able to explain everything. Thank you, and stay safe.